Hi guys, today we'll be talking about the Ex-meridian method. I actually made this video yesterday, but I realized that there was no sound to this video, so I'm remaking it again. This Ex-meridian method will be using Sun as a celestial body, and the future videos I will be using the star and the planets as well. So I'll put up an example about the star and the planets as well. But this video is only about the using Sun's altitude as the celestial body to calculate the latitude, observed latitude using the Ex-meridian method. Now, Ex-meridian method is when the body is not exactly on the meridian; it is very close to the meridian. So previously in my previous videos you must have seen the meridian passage, the Marpas method, which talks about the body being exactly on the observer's meridian, celestial meridian. But Ex-meridian is when the body is very close to the meridian. So the key word here is the body is near the meridian, as you can see in the question here itself. So whenever if you see a question which says that the body is near the meridian, it could be either reaching or normally it has passed. Sometimes people miss the meridian passage time, and then they can use the near the meridian time and or near the meridian altitude to calculate the observed latitude using the sextant altitude of the celestial body. So normally it's the sun. All right. Now the question says that it's 4th of March 1992. There is a DR position given. Sextant altitude's lower limb near the meridian is given as 56 degrees 19.8, and then the chronometer time is shown as well. The chronometer error is 1 minute 20 seconds slow. The height of I given is 12 meters, and the index error is 2.8 minutes on the arc. All right. What you would have to find is the direction of the position line or the PL and a position through which it passes. So when we say position, we basically mean the observed latitude that you will calculate using the Ex-meridian method and the dr long. So we use the dr long because the longitude is calculated using the long background method. So here, of course, using the Ex-meridian method, you will be calculating only the observed latitude. All right. So first, let me solve the ambiguity of chronometer time. Alright, so the chronometer time given to you is 11 hours 13 minutes 24 seconds. Now, like I've said in my previous videos, the chronometer works very similar to that of analog watch. So when you look at an analog watch and you see 11 o'clock like this, you don't know it's 11 o'clock in the morning or 11 o'clock at night. So many students ask me, why wouldn't I know? So we are talking about this is purely for academic purposes, for question purposes only. Especially when you're on the ship, you know what's going on. So the chronometer time, you know what is going on, whether it's night or day. But in this case here, of course, you don't know because this is for academic purposes, for question purposes only. So we assume we don't know whether it's 11 o'clock in the morning and 11 o'clock at night. So for that, we have to consider two cases. If it is 11 o'clock in the morning, and if it is 11 o'clock at night. So if it's 11 o'clock in the morning, it's 11 hours 13 minutes 24 seconds, and if it is 11 o'clock at night, then it's 23 hours 13 minutes and 24 seconds. Okay, then you apply your error. Your error is 1 minute 20 seconds slow, so you will write slow here, and if it is slow, you will add the error in both the cases, of course. All right. If it was fast, you would have subtracted the error, but if it is slow, you would add the error. Once you add the error, you can see that the GMT time that you get is 11 hours 14 minutes and 44 seconds, right? So, or 23 hours 14 minutes and 44 seconds. That's the GMT time. Then you have to apply the zone. Now, what is the zone? The zone you get from the LIT. LIT you get by dividing longitude by 15. What is LIT? LIT is nothing but longitude in time, and you get that by dividing longitude by 15. So 168 degrees 11 minutes, the dr longitude divided by 15 here. This is the dr long divided by 15 will give you 11 hours 12 minutes 44 seconds. Now when you write LIT, you write hours, minutes and seconds. But when you talk about zone, you round it off to a whole number. Alright. So this is for practical purposes only because on the time on the ship cannot be kept as per your individual longitude. It has to be kept as per a zone so that everybody can stay on the same time. Right. Otherwise things don't work practically. Now when it's less than 30 minutes here, you will round it off to 11 hours. If it was more than 30 minutes, you would have rounded it off to 12 hours. And that's why you have your zone as minus 11. Alright. Now why is it minus 11? Because when you are in west longitude, your GMT is ahead of you. The time at GMT is more than your time when you are in west longitude. When you are in east longitude, you are ahead of GMT. Your time is more than the GMT time. That's why you will subtract it to get your zone time. Now your zone time in this case is 001444 and this case is 12, 14, 44. So how do I know which is the correct time? Now if the zone time is also known as ship's mean time or SMT, that means this is the time that you are keeping on your watch on the ship. Now at that time, which is about 12 hours 14 minutes and 44 seconds, that is the time when you will expect the sun to be near the meridian. It might have just passed the meridian, that's why it's called ex-meridian, or it must be somewhere near the meridian at about noon time, ship's noon time. It cannot be midnight, so midnight you will not be able to see the sun itself, right? So that's why the second case becomes a correct case, and I will cancel out the first case. And as soon as you see that it's 12, 14, 44 on your ship, you immediately put the date as 4th of March, and then you think about whether the GMT is also 4th of March or not. And you will realize, yes, GMT is also on the 4th of March, because it's 4th of March, but it's 2300 hours. So GMT is ahead of you, but it's not yet the next day. It is not 5th of March yet. It's still 4th of March, 2300 hours, right? That's why your correct GMT becomes 4th of March, 2300 hours, 14 minutes and 44 seconds. This is the time that you will be using to work out the rest of the question. Not the ship's time, not the zone time. You will be using the GMT time. Alright. Now using this day and time, you will go into the nautical almanac and find out the GHA. So the GHA that you will find will be for 2300 hours. The increment that you will find, you will go into the increments page for, okay, this should be 44 seconds, not 4 seconds. Alright, these days I'm making some small errors in my solution. So yeah, I have to be careful. Alright, so 2300 hours, and then this increment, it will be for 14 minutes and 44 seconds from the increment page. And you always add the increment. Increment is never subtracted, it is added. So once you add the increment, you get your GHA for 2300 hours, 14 minutes and 44 seconds. In a short while, I'll show you where to get these values from the almanac. And so let me start with that. So I just want to know what else I can get while I get to do the almanac. So I can also get the declination. So the declination that you see here is for 2300 hours as well. Alright, and then you get your D value from the almanac page, and you go and apply the correction from increments page of 14 hours and 14 minutes and 44 seconds, and you will get a D correction value, and I'll show you what to do with all that. Alright, so let's get into the almanac for 4th of March. So I'll get into the almanac for 4th of March here. So this is what it looks like. So this is a 1992 almanac. So it doesn't matter what almanac you're using, the process is the same. The values will be of course different, but the process is the same. Alright, so you can see here, if I zoom in, you can see here for 4th of March, I have highlighted the GHA here as 162.6.4. The declination is 6 degrees 3.1 minutes south. Alright, and if you go down below, you can see the D value is given as 1. It's highlighted as well, right? The D value at the bottom of the declination column is 1. So these are the places you get your values from. Alright, now you also have to see that the declination from 2300 hours to 5th morning 00, it's decreasing. So for the D value of 1, you will go into the increments page, get the D correction, and you will subtract it, because you know that the declination of the sun is decreasing as you are going from 2300 hours to 14 minutes and 44 seconds. So now if I go into the increments page of 14 minutes and 44 seconds, you can see here. So 14 minutes and 44 seconds, and so if I erase this, all this here, so 14 minutes and 44 seconds, you can see is here is the increment, 14 minutes and 44 seconds, right? And for a D value of 1, you get a correction of 0.2 from here. This 0.2 is what you will subtract. So if you didn't understand, watch my other videos as well. In my other videos, I've shown you how to get the values from the almanac, and this is the one that I'm showing you again. If you think it's a bit quick for you, just go and watch my other videos as well. You will know where to get the values from. Alright, so we'll be using all these values here, and then I'll come back to the almanac again, because I have to visit the total correction page, which is normally the first page of the almanac. So I'll show that to you as well. I'll come back to this page. I have to come back to this page, and I'll show you where to get the total correction values as well. Alright, so before I do that, I'll erase all this so that when I come back here, you guys don't get confused. Alright, so I'll go back into the solution now. So you can see the increment here that I've used 3 degrees 41 minutes, and then I added the increment, and the declination also you can see it's 3.2. Then I subtracted the minus 0.2 correction for D1 that I got from the increments page, and I've got my declination corrected for 2300 hours 14 minutes 44 seconds. I've written down my dr latitude also for reference because I'll be using it for my calculations below. Now I go back to the GHA. Now GHA you see is 16547.4 and longitude you see is 16811 minutes. Now longitude west, GHA is supposed to be the best. That's the rule of thumb. The rule of thumb is if longitude is west, GHA should be more than LHA. If longitude is east, GHA is least. That means GHA should be less than LHA. But in this case, longitude is west, so GHA should be more than LHA. So how can I make my GHA more than LHA where it is less than longitude? So the only way I can do that, and for that I will have to erase this part here so that I can write it down. So what you have to do is you have to add 360 degrees here. Just add 360 degrees to this. So then this becomes 525, 47.4. And then you subtract 168 degrees longitude to get your LHA. So theoretically the GHA then is more than LHA. Get it? So whenever you see GHA is less than longitude, but you have to subtract, add 360 to it and make it larger than the longitude and then subtract it. So you will get your LHA. LHA, the rule is if it is between 0 to 180, it is west. If it is more than 180 to 360, it is east. So in this case, LHA will be east. So I will name it east. So again, if it is 0 to 180, it will be west. More than 180 to 360, it will be east. Alright. Then I go and start solving my sextant altitude. My sextant altitude is 56 degree 19.8 given to me in the question. Index error also given to me in the question is minus 2.8. Why is it minus? Because it was written as on the arc. When it is on the arc, you will subtract it. If it's off the arc, you will add it. So in this case, it was on the arc, so I will subtract it. I get 56 degrees 17 minutes. And the other thing I have to write down here, this is the dip correction for height of eye. So dip correction for height of eye, 12 meters. I'll go back into that page and I'll show you where I got my height of eye correction from. But before that, I'll also show you something called the apparent altitude. So once I subtract the height of eye correction, height of eye is always subtracted, never added, always subtracted. Once I subtract my height of eye, I get apparent altitude of 56 degrees 10.9 minutes for a lower limb of the sun for the month of March. So these are some of the things you have to remember, because once I go into the almanac, I'll again show you where I got the different values from. All right. So I'll go back into the almanac and so you can see height of eye for 12 meters, it's about here. This is the correction here. So this is the height of eye column. All right. And then the total correction column is here. This is the total correction column. But you have to remember, you have to note down the month. My month is March. So I have to go into this column here. And it's also lower limb. So this is the column I go. If it's upper limb, this is the column. But if it's lower limb, it's the middle column. For 56 degrees 10.9 will be somewhere between here, between 54.46 and 59.21. So this becomes my lower limb correction. There is no interpolation required. Alright, so these are the values that I'll be using again in the calculation. So here you can see the dip correction is minus 6.1 as I showed you there. You can go back and watch it if you didn't get it the first time. And then the total correction is plus 15.6 as I showed you before. Once you add it, you get the true altitude as 5626.5. Now I have named it south here. And you must be wondering how I did that. I'll come back to this later on. Alright, so let me calculate something called the MZX first and then I'll come back to it. I've also shown you that here minus 90, if you do minus 90 from true altitude, you get the true zenith distance. In some books, it's also written as TZD, is the same thing. And once I subtract 90 degrees, or rather I subtract true altitude from 90 degrees, I get true zenith distance as 33.5, which is also named north. And you're wondering how I've named it. Alright, so I'll show that to you. Although in this case, you will not be needing the true altitude. So I will cancel this out. You don't need the true altitude. The true zenith distance. You need the true altitude. You don't need the true zenith distance. What you need is something called the meridional zenith distance, MZX or MZD in many books. Now this is the scientific calculator formula for meridional zenith distance, MZX. That means it's very close to the meridian. That's what it means, and the distance from the observer's zenith to the body is MZX. Alright. The formula is cos TZX. Oh, actually you need cos TZX. So again, my apologies. I think these days I'm not on the best of my game, so I'll cut it out. You need the TZX. Alright. So again, you need the TZX to put in the formula. Right, sorry about that. So the formula says you need TZX, cos TZX, 1 minus cos P. P is nothing but your LHA, and then times cos of lat and cos of declination. P is nothing but LHA. Alright, so you can see that I've put the values of the true zenith distance here, and then I've put LHA here, 1 minus cos LHA, and then I've put the latitude and the declination values that I've calculated. Alright, follow the prompts that I have shown here you should be getting the same values in the calculator. I have stuck to about 5 decimal places. You can go more if you want, but minimum 4 to 5 decimals is good because it enhances your accuracy. The more the number of decimal places, the more is the accuracy. Alright, then you get cos mzx as 0.83409. Include any negative sign. If you get, you will not get any, but if you do, please include them. And then cos inverse of the value, you will get the meridional zenith distance, or mzx or mzd, whatever is written in the books, is 33 degrees 28.7. Alright, now I'll come back to the naming of the mzx and declination. So why I said before you don't need tzx, that was my mistake. You need it in the formula, but to calculate your latitude you don't need tzx, you need your mzx. Now how I have named mzx is very similar to how I name my true altitude in the meridian passage question. So if you have seen my meridian passage video, you will see how I have named the true altitude there and how I have gone on to name the others, but I'll show it to you again here. Alright, so for that I'll just erase some of the bits here so that I can show you here. So to name your true altitude, you basically name it same as your azimuth or bearing. Now what does that mean? That means you have to see where is the body of the sun bearing from you in the celestial sphere. So if you are the observer zenith, you are Z, where is the body bearing from you? So how do you do that? You basically draw a vertical line. Alright, now here we kind of make an assumption that the body is very close to the meridian. Alright, although it is not exactly on my meridian, I kind of make an assumption that it is very close to the meridian. So I can use this vertical line and put all the bodies or concerned parties on the same line. So firstly I will draw Q. Q is nothing but the celestial equator, also known as equinoctial. Once you draw Q, assume that you are on the celestial sphere. So what is your latitude? Your latitude is 27 degrees 18 minutes north. So you will draw it, go north of the celestial equator and put yourself there as Z. This is the observer zenith, that's you. Then what you do is you draw the latitude of the sun. The latitude of the sun is also called declination of the sun. And what is the declination? 6 degrees 3 minutes south. So you will go south of the equator and you will put X here. X denotes the celestial body. And now what you see is the body is bearing south of you. Body is south of you. You are north, body is south of you. So you will name it same as the bearing. So true altitude is named as south. That's why I named it south. Now when you are naming true zenith distance after that, you name it opposite to true altitude, which in this case becomes north. And you use the same rule for mzx. So when you are naming mzx, you will name it opposite to true altitude. Opposite to true altitude. So if you have named true altitude as south, you will name this as north. Get it? And then the declination is 6 degrees 3 minutes south. You put that there the way you have calculated. Then the rule of thumb is if they are different names, you will subtract it. So if they are north and south, you would subtract it. If they were both north or if they were both south, you would have added them. So because they are north and south and you have to subtract it, I will put a subtraction sign here and I will subtract the smaller number from the bigger number and retain the name of the larger. The larger is north here. So I will name the observed latitude north. And the answer I get is 27 degrees 25.7 minutes north. That's how you get your observed latitude. Then you use your dr longitude and that is the position through which the position line will pass. But you have to calculate your position line. And how do you do that? You have to calculate first the bearing. How do you calculate your bearing? Bearing is from the azimuth, of course. So to calculate azimuth, you first have to calculate the A component here. A is calculated as tan lat divided by tan p. Now you can also get these A, B values and C values from the northeast tables. But these days, because you have a scientific calculator, it's much faster to go through the scientific calculator. Alright, some of you may disagree, some of you may be very used to the northeast table. So please go ahead and use the northeast table. You should be getting more or less the same answer. So A is equal to tan lat divided by tan p, which is 12.34 if you put in the values. Please ignore any negative sign if you get. You don't have to include the negative sign in the final value. Alright, but you have to name it. You name it south in this case. Why? Because it is always named opposite to latitude unless LH is between 90 and 270. Your LH is not between 90 and 270. So you will name it opposite to lat. Latitude was north, so you have named it south. Alright. Second thing you calculate is B. B is calculated as tan declination divided by sine P. So I have put the values here. Tan declination divided by sine of P. Please ignore the negative sign again. And this time you name B same as declination. So if your declination is south, you name it south. Once you name your A and B, so again maybe I didn't mention this. P is again your LHA. So that's why I mentioned here P is LHA. Alright, so don't get confused. Once you get your A and B, put the values here, A and B, 12.34 south, 2.54 south. The rule is, if they are same names, you will add them. If they are different names, you will subtract them. So in this case, they are both south. So C will also become south and you will add them. So I have added them. Once I add them, I get C as 14.88 south. Then I calculate my azimuth. My azimuth is nothing but 1 divided by C times cos of latitude. Put the values, solve the denominator first, alright? Solve the denominator first and then solve the whole equation. You will get tan azimuth equals 0.07572 if you are sticking to 5 decimal places. Do a tan inverse, take the tan here, it becomes a tan inverse. You will get 4.3 degrees. I have rounded it off to 4 degrees. Why? Because it's bearing. So I need a round number because I sometimes will need to plot this bearing. If you continue with decimal, that's fine as well. Depends on your lecture, depends on what he wants in the exam. Please follow your examiner's instructions or lecturer's instructions. But for me, for practical purposes, if I have to plot this bearing, I need a round number. I cannot plot 4.3 on the chart, right? So once I get 4 degrees, I have named it south and east. How did I name this? Well, south comes from C. What is C? C was here. C is here. C. Whatever is your C will be my south. If it was not, I would have named it north. E comes from my LHA. I told you before, the rule is LHA 0 to 180 is west and more than 180 to 360 is east. In this case, your LHA was very close to 357 degrees, 36.4. So that's why your LHA is your, you name it east. Right? Once you name it east, you got south 4 degrees east, which becomes 176 degrees true. If you are wondering how, so this is north, and so let me show that to you. This is north, this is south. South is 180, east is 090. You don't need west here, so I don't worry about west here. South 4 degrees east means you go 4 degrees from south towards east. Right? Then this becomes 176 degrees true. That's how you get 176 degrees true of bearing. This is your bearing. To get your position line, just subtract 90 and add 90 to the bearing. If you subtract 90, you get 86. If you add 90, you get 266. That becomes your position line. So your position line is 86 to 266 degrees true. Alright, so hope this video helped. If you have any questions or if you think I have made any errors, please shoot me in the comments, rather write in the comments. I'll be happy to answer your questions. Alright, thanks, and thanks for watching my video. Really appreciating all the feedback that I'm getting from all of you.